What up, everybody? It's Mr. Troop. This guy right here. Yep, this guy. Yep, it's me. Oh, look at this cheese ball. Yep, this is the guy that is speaking to you. Can you hear my voice? Yes, you can. So check it out, guys. We have notes today. These notes are brought to you by my apartment complex. So take out your books, turn to page 96, and let's get started with polynomial functions of higher degrees. All right, so here we go. I'm gonna lock this in here. I hope you guys can see what's going on. I kind of cannot, so we're just gonna do the best that we can. All right, so check this out. Why is this graph discontinuous? Well, it's pretty obvious because right here, I had to pick my pencil up. Yep. If you want to classify, this is called a jump discontinuity. And over here, this function, kind of similar, but it's a little bit different as to why it's discontinuous. This line is going like all the way up, and this line is going like all the way down. And this line right here isn't actually part of the graph. You guys know that though. This is called a vertical, say it with me, class. It's called a vertical asymptote. So this is discontinuous, and it is called an essential discontinuity. Okay, an essential discontinuity. Check that out. You guys doing well? Awesome. All right, so this graph right here is it's continuous. That's fantastic. It's really easy to tell. It goes on forever. It's got a domain of all real numbers, a range of all real numbers. At any point in time, I never once have to pick up my pen. My pen can just draw this nice, smooth, and fluid line forever and ever without ever stopping. I never have to pick it up and move it to another location. It is continuous. And I want you guys to pause this video, take a moment, and write down why it's continuous in your own words, okay? I used my words just now. I want you to try it. Same thing for this graph. Pause the video and write down why this graph is continuous, okay? And I'll see y'all in just like, I don't know, however long it takes y'all to do that. All right, welcome back. I'm glad that you guys paused the video. Let's talk about graphing functions. Okay, your book calls this below information the leading coefficient test. The book also calls the leading coefficient of a polynomial function a sub n. That's pronounced a sub n, okay? If the degree of a polynomial is an odd number, for example, 1, 3, 5, 7, 9, 11, you guys know the drill, then the n's travel in opposite directions. Okay, and so take a moment and think about that. If I'm odd, if I have an exponent that is odd, my n's travel in opposite directions. You guys are familiar with the graph y is equal to x cubed, correct? Y is equal to x cubed. This graph starts down here, and it goes up there, right? It starts in one direction, and it ends in the other. They go in opposite directions, okay? So explaining what this graph should look like, well, we want to look at the leading coefficient, or sorry, the leading exponent right here. The leading degree, the power. So the leading exponent, the power of this polynomial is 5, okay? So I'm going to say power of 5, which is odd. Now, I don't mean odd as in like peculiar. I mean like it's literally an odd number. So therefore, this graph right here needs to start in one direction. And no, I'm not talking about the hip and popular band featuring Harry Styles. I'm talking about directionality, as in downwards versus upwards. It's going to start in one direction and it's going to end in the other direction. Feel free to grab a calculator right now, pause this video, grab a calculator, graph it if you'd like, and see if I am lying to you or if I'm actually very much telling you the truth. So go ahead and try that out. Pause this video and try it out. All right, welcome back. I'm glad you paused the video and it worked out, and I'm glad that I didn't lie to you. So check this one out, okay? It says if the leading coefficient, remember coefficient, that's the term for the number in front, the number, the sidekick, the number that is right in front of my letter X, is negative, then the right side of the graph falls, means it goes down, and the left side of the graph rises, meaning it goes up. So this one has a negative coefficient, right? Let's write that down. Negative coefficient. Negative coefficient. Woo! And it's an odd power. Therefore, this guy is going to look something, and again, this is not a Picasso painting or anything, but it's going to look something like this. It's going to start up, and it's going to end down. We're going to just completely flip them things around. Okay, change the way we look and think about things. I assume you guys can see that. If you can't see that, I'm really sorry, but there it is. Okay. All right, if the degree of a polynomial is even, then the ends travel in the same direction, okay? Kind of like a quadratic or a parabola, x squared. That's really, really, really popular. We think about x squared a lot when we think about even powers, okay? Y is equal to x squared. We know what that looks like. It's a parabola. The ending points go in the same direction. They both go up, right? Okay, so same thing with this one. It's to the power of 6. Now 6 is an even power. This has an even power. Therefore, my ends are both going to go up. Now it's going to do some like wiggly stuff in the middle, and we'll talk about that in just a little bit. So if you graph this in your calculator, you'll see that it does do some wiggly stuff. But at the end of the day, both ends are going to go up. Both ends are going to go up. Okay, y is equal to negative. Okay, so this is a negative coefficient. Let's write that down. Negative coefficient. There, and it's an even power. That means both of my ends are going to go in the same direction, but that direction, because it's negative, is going to be down. Okay, we're both going to go down. Now this right here, this is the bread and butter, man. This is, if you take my calculus class next year, which you all should, this is what we're talking about. Okay, a fancy way of expressing, let's change it to expressing this. Oh man, big also, man, look at this. This is like a big hint, such a big hint that I'm gonna grab a different type of pen. What you'll be expected to use, AKA test question. Boom. That's a freebie right there, you guys. You should get these questions right, because I told you it's going to be there. Don't let me down. All right, so if we are increasing, this says is my x values. My x values go to negative infinities, then my y values go to positive infinities, okay? If my x values go to positive infinity, then my y values go to positive infinity, right? We're talking about increasing, okay? My x's get bigger, my y's get bigger. My x's get smaller, my y's still get bigger. It means we're going up. It's a fancy way of describing up because infinity is up, right? When y approaches infinity. Remember, f of x is another way of saying y. Decreases. It's literally the exact opposite. As my x's go to the left, my y's go to negative infinity, so down. So x's go left, y's go down. As my x's go right, y's also go down. That's decreasing, okay? Awesome, all right, so check this out, guys. Sketching more accurate graphs. We want to sketch the most accurate graph that we can, but sometimes we don't have a calculator, so we have to really, really, really be good at what we're doing and understanding what's going on, okay? So we're going to review some terminology from Algebra 2. Remember, back to learning about quadratics and other polynomials, you would factor each polynomial to find the factors. You would then use the zero product property and set each factor equal to 0. That's what your homework page 90 was all about, factoring. And then we saw on page 91 or 92 the zero product property that was setting it equal to 0, setting each piece equal to 0, and finding the factors. Okay, this would yield an x equaling some value. This is something very special because that is a 0 or a root. Remember, guys, what's another word for 0 or root? X-intercept. X-intercept. Okay, or you could call it a solution. You remember in class I said I didn't really like the word solution, but that's okay. Awesome. All right, so let's check this out. Here we go. Let's say you factored some polynomial, x minus a to the power of k, meaning you have a x-intercept. You have an x-intercept when x is equal to a. If your exponent k is odd, the graph of this polynomial would touch the 0 and continue on. In other words, it crosses. That's the important part. It crosses the x-axis, okay? What we're talking about right now, you guys, that we're learning is we're talking right here, multiplicities. It's all about looking at the power. Is the power even or is the power odd? Multiplicities that are odd and greater than 1, the graph curves to that point. I like to say it wiggles. Okay? If k is even, the graph of this polynomial will touch the 0 and it will bounce. It will bounce back in the direction that it came from. In other words, it does not cross the x-axis. K is known as the multiplicity for the 0. This, man, you probably just read a mouthful and you're probably thinking like, man, what on earth does that mean? But hang with me, we're gonna look at some examples, okay? Awesome, so check this out, ready? As we went through -2, we had an x-intercept at -2. I'm going to write the equation. Okay, so let's use this graph as a practice problem. That means I had to have an x plus 2 as a factor because I have an x-intercept here at -2. I have an x-intercept here at -1. That means I have to have x plus 1 as a factor. However, did I cross the line or did I bounce back from the line? Well, as you can see, I kind of bounced back from the line. That means this is going to have a multiplicity of 2. It's going to have a multiplicity of 2. And the last x-intercept that I have is over here at 2. That means I had to have x minus 2 as a factor. Now, check this out. Remember how I said it curves or it wiggles through the point? Is this one right here goes straight through. It goes straight through, right? This one bounced. This one right here, it has a little wiggle. It's got a little shimmy in it. And look at it groove. It's like a little dancing function. It's just all like, uh-oh, uh-oh, you got it, you got it. Y'all can't see me, but I'm like dancing in my apartment right now. So here we go. My wife's making fun of me. That's okay. That means this is going to have a multiplicity of 3 because it looks like the cubic function. We can look at this cubic function and understand that it has to have this multiplicity of 3. Throw a y equals in front of it, guys, and you just created the graph of this function. If you don't believe me, pause this video, plug this into your calculator, and see if it looks kind of sort of like that picture. It might be a little off. We may need to stretch it or shrink it, I don't know. But I bet you all the x-intercepts will look exactly like that. One will go straight through, one is going to bounce, and one is going to wiggle. So try that now. Go ahead and pause it. Welcome back. I'm so glad that you paused the video. I hope you had a nice time away from me. I'm glad it worked out. See, I didn't lie to you. You used your calculator, you graphed it, and it looked good. All right, so check this out. Let's talk about turning points. Given a polynomial function f of x of degree n, the following statements are true. The function f has at most n real zeros. Now look at that. This is the same n as this n, okay? The same n as this n. Degree n, that means like x squared has 2 real zeros. X to the third has 3 real zeros. X to the fourth has 4 real zeros, and so on and so forth, okay? That means the graph has one less turning point. Now, turning point is interesting. A turning point is when our graph turns around, okay? It's going to turn around at these points. Our maxes, our relative maxes, and our relative mins, okay? Relative maxes, and, oh, that's not one. I don't know what I'm doing there. Relative maxes and relative mins. So looking at this one, for example, I have 1, 2, 3. I have 3 x-intercepts. Now you may be thinking, okay, that means this is something to the power of 3, like y is equal to x cubed, because we said zeros. Remember the word zeros, you guys. Zeros is another word for x-intercept. But it says at most. This is what I need you guys to highlight right here. At most. Does it mean we have to have that many? No, not at all. If you look at the cubic function y is equal to x cubed, it only has 1 x-intercept, okay? We're saying it could have up to 3. So we had 3 x-intercepts, but this obviously is not a cubic function because they travel in this, my endpoints travel in the same direction. Do y'all see how the endpoints are both going down, right? Well, if the endpoints are traveling in the same direction, this has to be an even function. So y is equal to x squared, or to the fourth, or to the 6th, 8th, 10th, something like that. So let's count the turning points, okay? This is my turning point. Okay, I'm gonna write a little TP right there for turning point. This is a turning point, a little TP for turning point. And this is a turning point. So what we just said is we have 3 turning points. And my turning points are n minus 1, right? So that means if I were to add the 1 to both sides, this power, this polynomial could have had a power of 4. So this is some y is equal to x to the 4th, right? Now, not exactly that. It's been moved a lot, okay? We could even try to put this together. We have here x plus 3. That is one of our factors. So y is equal to x plus 3. And it goes through it nice and straight. So it's multiplicity of 1. Right here you have your x plus 1. Okay, now it bounces, right? Do you see how it bounces like a basketball, right? Bounces like a basketball. So it had a multiplicity of 2. And here we go, this guy right here, y is equal to x minus 3 to the 3rd power, because it didn't bounce, but it didn't go straight through. It really kind of danced its way through. It wiggled a little bit, right? Now, if we were to count my x's, I have 1x, 2, 3, 4, 5, 6. So in reality, this is a y is equal to x to the 6th function. So yeah, that means our guess of x to the 4 was incorrect. That was absolutely incorrect, okay? So that's where we need to come back here and also acknowledge this said at most, right? I'm making small mistakes on purpose, guys. I want you guys to see the importance of the words at most. It does not guarantee. So what we just did right there is great. It could have worked for some polynomials, but not for all the polynomials. Okay? All right, let's see what else we got. We are rocking and we are rolling. We are snow patrolling. A boom, boom. Chicka boom. Here we go, y'all. Here we go. Okay, so let's graph. Here we are. I got f of x is equal to 3x to the 4th minus 4x to the 3rd. Now, first thing I see and that I don't really like is the way this is written. It's in kind of a standard form. Let's go ahead and factor it. I know we're pretty good at that. We've had a lot of practice, okay? So I'm going to write, not 3. I'm going to write y is equal to, I can factor out an x cubed, and that's going to leave me with a 3x minus 4 left over. Do you guys agree? X cubed on the outside, 3x minus 4 left over. Okay, so then let's go up here. Let's do all the steps. We got steps. Okay, so my first step, determine the end behavior using your rules and your leading coefficient, okay? So I have a positive, oops, sorry, I'll move over, coefficient, and I have an even power, the leading power, even power, positive coefficient. That means I need to go up with my end behavior, both directions. Both my directions need to go up. Okay? All right, step number 2, find the zeros of the polynomial by factoring. That's why I wanted to factor. Okay? That means if we were to set this equal to 0, I have 2 math problems. I have the math problem that says x cubed is equal to 0, and I have the math problem that says 3x minus 4 is equal to 0. Well, that means x is equal to 0 and x is equal to 4/3. Those are my x-intercepts. These right here are my x-intercepts. All right, and step 3, find a few extra points using a number line or some test points. Yeah, this is a smart idea, okay? So we have a couple of points, 0 and 1 1/3. So here we go. I'm gonna graph this. I'm gonna put a dot right here at 0. Boom, just like that. That's my first x-intercept. And then I have a dot here at 1 1/3 or 4/3. I'm gonna put my dot as close as I can to there. Now, I know that we have to wiggle. We have to wiggle when we go through this 0. All right, so let's write a little note down. Okay, that power of 3 tells me to wiggle. And this is really a power of 1, isn't it? So we're gonna go straight through, okay? So here we go. I got to wiggle. Now, man, this is kind of tight. It's kind of a tough graph. I'll tell you what, before we do that, just to make it a little easier on us, let's pick some points, okay? So give me an x, y table here, and let's pick some points. I'm going to pick the point -1, 1, and 2. I'm going to pick the point -1, 1, and 2, and we're going to plug this back into the original function, all the way back to the original. Okay, so -1 to the 4th is 1. 1 times 3 is 3. -1 to the 3rd is -1. -1 times -4 is +4. So that's like 3 plus 4 is 7. Please feel free to use a calculator on that. I could be wrong, actually. If I am wrong, someone pause the video and correct everybody. Again, sorry about that. All right, if I do a +1, ready, that's going to be 3 minus 4. That's going to equal -1. And then the 2, this gets kind of big. It's like 16 times 3, which is 48. And 8 times 4 is 32. 48 minus 32 is like 16. Kind of a big number. So we could try to put some of these dots. So like -1, 7. It's really big. 1, -1, not that bad. And then 2, 16, it's like way up there. So this is a challenging one to graph because it's really, really, really skinny. Let's do the best that we can. Remember, we're not going to go straight through though, are we? No, we're going to wiggle. Do you see I kind of got a little hitch in it? And then I'm just going to turn it right around. And we're going straight through, and then we're going to go super high up and throw some arrows on it. Okay? So as you can see, it's got a tiny little wiggle through the 0, and it goes straight through the 1 1/3. Okay? Oh, that was tough. Okay, let's look at this one. This one's actually way easier, even though it looks a little bit more complicated. Let's get my steps. Step 1. Okay, this has a negative coefficient. This is the giveaway right here. Negative coefficient. There's a dog barking. I don't know if you guys can hear that. It's a big dog. He's clearly seen a cat, and he's just barking at it. Okay, we have a negative coefficient. Now let's count our power. Okay, I need to count my power. So here we go. This is like to the power of 1. This is to the power of 3, to the power of 2. Okay, I'm going to add all these numbers up. So my power is 1, 2, 3. Let's add all those up. 1 plus 2 plus 3 is 6. Is that an even number or is that an odd number? You guessed it right, you guys. That's an even number. We have an even power and we're negative. That means we are going to travel down in both directions at the end of my function, okay? So here we go. Let's pick out these x-intercepts. Let's pick them out. Here we go. Number 2, my x-intercepts. I have an x-intercept here at 1. I have an x-intercept here at -2. Remember, I'm just setting these equal to 0. And I have an x-intercept here at, guess for it, +4. Good. So here we go. I got an x-intercept here, -2. X-intercept here at 1. X-intercept here at 4. These are my x-intercepts. Now, let's check my multiplicities. When we go through 1, we're going to go straight through it. When we go through -2, I have to wiggle. Feel free to label these, right? This is my straight through. This is my wiggle. And this right here is, well, it's a 2. That means we're going to bounce, okay? So we got a straight, we got a wiggle, we got a bounce. So I'm going to do this kind of the best I can. I know we got to go down. We got to go down to the left. We got to go down to the left. Okay, and at -2, we're going to wiggle. So I'm going to draw a little bit of a wiggle here. Do you guys like my wiggle, my little dance move? Like, man, this is a hip and happening function. And then it's going down. Okay, so it has to turn around somewhere. We can kind of create a little bit of a table if we'd like to. This is the best way to do this. Pick some points. I'm just going to pick 1. I'm just going to pick 0. If I plug a 0 in here, I'm going to get -3 times -1 times 2 cubed times -4 squared, which is kind of crazy to look at. So let's just take a moment. That's +3 times 8, which is 24 times 16. Yeah, that's a really big number, you guys. It's so big, I don't know what it is. Let's just write big number. So this function goes up a lot. It goes up, like, if you were to graph it, it probably looks like it goes up, like, forever, you know? So just for the benefit, let's pretend like it equals, I don't know, 6. I know it doesn't, but let's just pretend, okay? So then we're coming back down to 1. But now, what did we say is going to happen at 1? It's going to go straight through, right? Straight through. Okay, no wiggle, nothing like that. We just went straight through. Okay, now I gotta go over to this 4. It's gonna have to turn around at some point, right? It's gonna have to turn around. And when we get to the 4, are we gonna go through it or are we gonna bounce? Well, we said over here that we're gonna bounce. So we're gonna come up here, hit it, and go, right? A little pick and roll action for you right there. Okay. Now, where this point is, again, we could have found it out. I could have set some numbers. I could have plugged in a 2 if I wanted to. And that would have given me -3 times 2 minus 1 is 1. Times 2 plus 2 is 4. Don't forget the cubed. Times 2 minus 4 is -2 squared. And again, that's also going to be a very large number, because 4 cubed is 64 times a bunch of stuff. Big number, so it probably goes way down. So if you graphed it in a calculator, it does not look exactly like this, but this kind of gets the memo across. Do you guys kind of see what I'm saying? If you zoomed out a lot, it would eventually look like that. But this is all about the end behavior. I was even and negative, so I had to go down. I had to wiggle through this point, go straight through this point, and I had to bounce at that point. Good work. Alright guys, I'm going to pause this video and make another one because this one's getting kind of long. So make sure you're taking these notes, make sure you're up to date, and I will catch you guys on the next one. Oh, this is going to feel like it's falling. Hold on. Draw.